Paul, if you want to scoot over there. Okay, so this is our first prototype that we're going to demonstrate. It's an educational tool, and it demonstrates the load current delay, which I'm going to explain later on. But in this prototype, we have two ReGenX coils that are in the core of the shape of the core that's in this is an E-core. So we have a ReGenX coil on the inside, actually two of them, the yellow wire and the green wire, and then we have a conventional coil on the outside which delivers the electric power to the light bulb. And the point of this prototype is to show the load current sine wave for the conventional coil and the load current sine wave for the ReGenX coil, where both coils are being excited by the same magnets on the same rotor in the same time domain. And they also have the same load. So if everything is the same, but the ReGenX coil is operating differently, we will see the load current sine wave for the ReGenX coil is displaced by 45 to 50 degrees and then 90 degrees. Okay, once you understand what the load current delay is about, and you can analyze it and you understand what's happening, and I will show you that in a second, well, as we go through, you will be able to understand where the acceleration comes from, where the decreased prime mover input requirement comes from, and where the infinite efficiency operation comes from. Okay? So if you guys can come over here, because I'm going to run over there. And we have our oscilloscope where we are looking at the conventional coils sine wave, the ReGenX coils sine wave. We have a power analyzer and a tachometer so we can monitor the speed. And when I put the conventional coil on load, the conventional generator coil, we will see system deceleration, and we will see the prime mover input is going to go up because the prime mover is delivering additional mechanical power to the drive shaft. That's conventional generator operation, and when I put the ReGenX coil on load, the prime mover input consumption will drop to less than what was required at idle. Okay, and the speed will increase to above what the system was idling at. What's important to note also in this demonstration is that we're starting at what's called steady state speed. Okay, at a steady state speed, the power in the drive shaft going from the prime mover to the generator, the power in the drive shaft is the torque times the speed. At what's called rotational equilibrium, that's a steady state speed, the net torque in the drive shaft is 0, and so the power is the torque times the speed. If the torque is 0, the power is 0. So that's why there's no power in the drive shaft when it's idling at steady state speed. That's why when the generator is placed on load, you need to add more mechanical power to the drive shaft, otherwise it will stall. Okay? All right. Okay. And here we have the output across our Okay, you can see everything. So we're at so we have 150 watts to our prime mover. We're at the speed is 3,488 RPM. We're on no load right now. We are on what's rotational equilibrium, steady state speed. And we're going to deliver about 10 watts to the load. Okay? And whatever we take from our conventional coil, this number has to go up by at least that and more. Okay? So we're at 148. And if you want to come in, you can come in closer. We're delivering 10 volts across the load, 1 amp, which is about 10 watts. We've gone up to 165. So we started at 150, 148. Let me show you no load again. 147. So we're at 164. The speed has also dropped slightly, and we can see the load current sine wave for the conventional coil on the oscilloscope. Okay, I'm going to put the ReGenX coil on load. So again, pay attention to this and the current, because I'm going to introduce you to flux harvesting. Okay, that's an important concept.
This is why you think about the top.
Okay, so the output of the conventional coil has gone up a little, slightly. Our input is down to 145. That's less than what we started at idle. And we can see the green is the load current sine wave for the ReGenX coil. So I'm going to put it on to conventional operation again. And if you just watch the light bulb, you'll see it go brighter. What that means is we're taking the discharging magnetic flux from the ReGenX coil, we're feeding it into the conventional coil so that we have rotor flux and electromagnetic flux from the ReGenX coil influencing the conventional coil's output. So you go a little brighter, okay?
And the RPM is here a lot, right?
The RPM goes up, and the input to the prime mover goes down. So now the ReGenX coil it's basically overriding the generator armature reaction produced by the conventional coil. So now I'm going to engage the second ReGenX coil in the prototype. So again, we're at 142. So now it's down to 138. It's 10 watts less than where we started. And we're delivering 10 watts to the load end. The load current delay can be between 45 degrees. Now it's 90 degrees, okay? So this is the load current sine wave for the conventional coil in purple. And the load current sine wave for the ReGenX coils is 90 degrees delayed. Delayed in the time domain. It's both loads are purely resistive loads. So that means the current and voltage are in phase. So it's not a phase angle differential, it's a load current delay. So again, this is the load current for the conventional coil, but the voltage is in phase with the current, and the same thing applies with So introduction to load current delay, very important thing to understand. And small introduction to flux harvesting. That's another component of the innovation that becomes more and more important as we go further down. And let's go back. Go back to low load again. So, again, all generators on the planet work on the same principle. If you want to take a megawatt on your output, or 10 watts, or 1 watt, or any amount, you need at least a megawatt of additional mechanical power going in. Whereas the ReGenX generator says that's no longer the case. In fact, you need less mechanical power going in, less mechanical power than was required at idle. And at idle, the mechanical power, which we already established, was 0 watts. You need less than 0 watts. Is that clear? Is that clear? Okay. Yeah, it's just the beginning. Just the beginning.
Oh my God.
Okay. So what I'm not gonna do is leave you hanging with the understanding. Once I'm done the demonstration, I'll explain so you can